Okay. So a radian is the angle swept out by traveling one radius of arc length along the circumference of a circle. Along the circumference of a circle. Okay, that's really the definition of a radian. And I gotta tell you, when I was in high school, I don't remember that was what the definition of a radian was. To me, I always knew that there were 2 pi radians in a circle, but I had no idea why it was 2 pi radians. It's so let's actually draw this so that we can conceptualize it a little bit more. So here, this pink line that I have drawn is the radius of our circle. And if we pick up that radius and we instead lie it along our circumference, we would see that it would cover about that much arc length. Right? So this thicker pink line along the circumference is still one radius for me. And if we look at how much angle I have swept out, so if I kind of do a little, right, if I kind of make this into like a pi wedge, the angle that you have swept out, so this angle right here, that is what we're talking about when we say 1 radian. Okay. There is a very cool graphic in the 8.1, or no, sorry, not the learning page. Here we go. We got 2 little cool things from GeoGebra that do definition of a radian. So I'm going to optimize for a video clip and hopefully you guys will be able to see this. This is, again, this is linked in today's date. It's the definition of radian 1. It's a GeoGebra thing. And what it does is it, again, tries to reinforce like what really is a radian. So we have this red line, and this red line is the radius of the circle. And we can watch that radius go out to the circumference. And every time it travels out, they just change what the color of the radius is. But you can see, right? Like we can see that we can fit 1, 2, 3, 4, 5, 6 full radii around a circle. And then we're left with a little bit. We have a little bit left over. And the little bit that we have left over is 0.28 of another radius. So we can fit approximately 6.28 radii around that circle. And if we were to figure out exactly how many radii, not just 6.28, but exactly how many that is, we would find that it is exactly 2 pi. So that's what your math teacher is trying to describe to you when they say that there are 2 pi radians in every circle. It means that we can fit 6.28 radii as we travel around the outside of our circle. And it doesn't matter what our radius is. So we can make our radius like much, much smaller, right? We can make it 2 instead of 5. And we would find that we trace out the exact same number of radii as we go around. Okay. This is a really important conceptual understanding for us because we're very used to dealing with lengths. So we're very used to dealing with things like, you know, how many meters is this radius? And we want to be able to translate that into how many radians have I really traveled through. So I think this is a really, really helpful way to link those two things together. Okay. Wait, can you talk about the small part again? Oh, this little bit that's not covered by a radius. So this little bit, right, is not covered. We don't have enough for a full radius right here. But if we wanted to figure out how much of a radius would fit in there, we could just find, you know, what arc length is left, how big was my radius? Okay, another 0.28%, right? Another 20, or sorry, not 0.28%. This percentage that's left uncovered is 28% of another radius. So that means that we could fit 6.28. Why is it 0.57 divided by 2? Because I set my radius to 2 and the graphic just told me like, hey, this is how much of your circumference is uncovered. It's 0.57, you know, meters or whatever. That number changes, right, as I change the radius. So the actual length of circumference that's left uncovered changes if you make the circle smaller or you make the circle bigger. But what we notice is that the percentage that's left uncovered always stays the same. It's that 0.28. Yeah. Okay. I'm gonna go back to the notes. What? Okay, cool. I don't think I need to optimize for video anymore. Okay. Okay. Another thing that I want to make sure that we understand when we are talking about a circle, another definition is not only of what is a radian really trying to describe to you, but also what is being described when we talk about a rotation. Because we're going to see that word rotation a whole bunch. Okay, so what is a rotation? A rotation is one time around the circle. So if we travel around our circle once, we have completed one rotation. If we travel around our circle 14 times, we have gone 14 rotations. And because, you know, we're moving, but we're not necessarily changing our position all that much, it's important to use, or it's important to understand like what is trying to be described to you, right? Even though we're not necessarily ending in a different spot than where we started, we're still traveling some distance because we're still traveling through some rotations. Now we can relate rotations and radians to each other because one rotation, right, one time around the circle occurs when we sweep out 2 pi of radians. Right, just as we saw on that cool GeoGebra thing, was that we sweep out 2 pi radians with every single rotation. Okay. You guys feel comfortable with those parts of the circle? All right, fantastic. In that case, let's start describing some angular motion, okay? And when we want to describe motion, we usually think about like how far we go, how fast we're moving, and how much we're speeding up or slowing down. So when we think about how far you are traveling when you go around the circle, in physics, we would say that you are describing your angular displacement. Right? We are already familiar with that word displacement from our linear study. We know that displacement is really trying to describe to you like how far you go. So how far you go around the circle is your angular displacement. Now the symbol that we use to describe this is the same as what we would use to describe an angle, right? Because when we are traveling around a circle, we're really sweeping out an angle of our circle. So we may describe that as a change in angle, or some people just prefer to write theta by itself. They don't necessarily include the delta in front of it. And the unit that we are going to use to describe how far we've gone in our angular displacement is going to be the radian, right? We want to describe how far we have moved around our circle. Have we moved 1 radian? Have we moved 2 pi radians? Have we gone many, many rotations? So maybe we're going like 4 pi radians, 6 pi radians, all that kind of stuff, right? All of that is going to be describing how far we've gone around our circle, or even how far we've gone around the circle multiple times. Okay, let's talk about how we can talk about how fast you travel, right? Because we can move in this rotation very slowly. We can move through rotations very quickly. And so how fast you are rotating is your angular velocity. Okay, or if we don't care about the direction, if we don't care if it's clockwise or counterclockwise, we would call it angular speed, right? Because velocity has that direction component to it. Speed has no direction. But both of them are trying to describe to you basically how fast you're traveling. So the symbol that we are going to use for angular velocity is a Greek letter. It is the lowercase Greek letter omega, which looks like a curvy little w. Kind of like a curvy little w is the lowercase Greek letter omega. And the unit that we will use is radians per second, which can be abbreviated to just rad per s. Here, I'm going to write that part in angular displacement. That radian can be abbreviated with rad. Okay, and then the last thing the last quantity that we want to use to describe angular motion is basically trying to describe how much you're speeding up or how much you're slowing down. So that is an angular acceleration. Right? We know that that's kind of what acceleration is describing to us. Are we speeding up? Are we rotating faster and faster and faster, 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 faster as we go? Or conversely, are we rotating and then we slow down in our rotations? Okay. Those are both examples of some angular acceleration. And we will use another Greek letter. We will use the Greek letter alpha to symbolize angular acceleration. Kind of looks like a fish. And we will use the unit radians per second squared. Okay, which also can be written as rad per second squared. All right. So these are a lot of the words that we're going to be using today. And crucially, these are the symbols that you guys are going to be seeing. Okay, so we're going to want to familiarize ourselves with them very quickly. Now, I am going to take a slight diversion. Oh, I thought that alpha symbol meant proportional. It does. We only have so many letters and so many alphabets, so sometimes they get reused. But yes, this in the case of angular kinematics means angular acceleration. Sometimes if we replace an equal sign with this thing, it means proportional to. So it means both. But what I would like to do is I would like to take a slight diversion. This will be fast, I promise, and it will be worthwhile. I want to do a little compare contrast between linear acceleration, centripetal acceleration, and angular acceleration, because very quickly here in the course of like 2 weeks, we've gone from having one kind of acceleration to having 3, and that's a lot. So I just want to remind you that when it comes to things like linear acceleration, we're talking about the fact that we speed up or slow down in a straight line. That's linear acceleration. You got to be speeding up or slowing down, and you got to be doing it in a straight line. Centripetal acceleration, which was brand new to us in Unit 7, occurs when we keep the same speed. And what centripetal acceleration does is it allows us to change direction. Okay, so we are not speeding up or slowing down when we think about centripetal acceleration. We're just thinking about that changing direction thing. And then lastly, angular acceleration, right? So now with angular acceleration, we are back to speeding up or slowing down. And this is describing when that speeding up or slowing down occurs in a circle, right? So we have some things that are similar, right? Linear acceleration can describe speeding up or slowing down. Angular acceleration can describe speeding up or slowing down. Centripetal acceleration can happen in a circle. Angular acceleration can happen in a circle. But the combination of whether or not you're speeding up or slowing down and whether or not you're moving in a straight line or a circle is unique to every single one of these. Okay. Okay. And as long as we are here, kind of talking about the different kinds of motion that we are already familiar with, let's make a connection between linear motion and angular motion. Okay, because this connection between linear motion and angular motion is going to allow us to then come up with our angular kinematic equations. So let's start by talking about displacement. Okay. So let's talk about displacement. When we talk about linear displacement, we were talking about delta x, right? And now in the angular frame, we're going to be talking about delta theta. Okay. Now these two things can be connected to one another. So if we think about a circle, if we think about moving along that circle, so maybe we move like, stop it, there we go. Ooh, okay, we move that far around our circle. Okay. That arc length would be our, ooh, I don't want the pen to be that thick anymore. That arc length is our linear displacement, right? And the angle that we have swept through is our angular displacement, right? So arc length is linear displacement, angle is the angular displacement. And these two things are directly related to each other, right? The more arc length we travel across, the more angle we're going to sweep out. And the reverse is true, right? The more angle we sweep out, the farther our arc length becomes. So these two things can be connected to each other. And we're going to draw that connection by thinking about what happens during one rotation. So let's assume one rotation. And if we assume that we go through one rotation, then we know the arc length, right? So our linear displacement will be the circumference of the circle. It's going to be 2 pi r meters. And the angle that we will sweep through, so our angular displacement, is going to be 2 pi radians. And if you look, we could substitute in our angle into our linear displacement. And it would yield for us delta x equals delta theta times r. Since delta theta was 2 pi, we're just sticking that in for this 2 pi right here. So we can write that, right? We can write that. We can say that in general, anytime we want to relate our linear displacement and our angular displacement, they relate to each other as linear displacement is equal to angular displacement times r. Now, just a little FYI, they do not put this on the AP Physics C equation sheet, this relation. It's not there. But I still think it's really helpful for us to know, okay? Now let's try to relate linear velocity and angular velocity. Okay, so when we talk about linear velocity, we're talking about v. When we are talking about angular velocity, we're going to be talking about omega. And again, right, both of these things are trying to describe how fast you're moving, right? So how quickly did we sweep out our motion, right? Did I do it slowly? Or did I do it really fast? Again, just like how the linear and angular displacement were connected, linear and angular velocity are connected as well. So again, let's assume that we move through one rotation. If we go through one rotation, then our linear velocity is going to be our circumference, 2 pi r, divided by our period, right? The amount of time it takes. Hopefully you guys recognize that linear velocity equals 2 pi r over capital T. You recognize that from last unit. For angular velocity, right? If we assume one rotation, we will have moved through 2 pi over the course of the period. And yet again, we see that we could do a lovely substitution to relate these two quantities to each other. V equals, and instead of writing 2 pi over t, I could replace that with omega. And what we end up with is we end up with linear velocity is equal to angular velocity times r. Linear velocity is equal to angular velocity times r. And I'm sure you guys guessed it, this is not on the equation sheet either. right? This is not provided to you on the AP Physics C equation sheet, but it is a very helpful thing to know. And then the last one that we can relate is acceleration. So linear, we're talking about little a. For angular, we're talking about alpha. And if we define linear acceleration, we know linear acceleration can be defined as your change in velocity per change in time, which, since we know that linear velocity is equal to angular velocity times r, we actually could write that as change in angular velocity times r over time. Now, angular acceleration is defined as the change in angular velocity per change in time. And yet again, we can see that that definition can get substituted in to our linear acceleration. And so we would get that linear acceleration is equal to angular acceleration times r. And I will write it one more time. This relation, that bad boy, not on the equation sheet. All right. So let's take a second and do some examples now. Okay, because we've talked about a lot. We've talked about parts of a circle that are going to be relevant for us as we talk about moving in a circle. We've talked about how we can describe what that motion looks like, right? By defining angular displacement, angular velocity, angular acceleration. And we've talked about the fact that there is a connection between linear and angular motions. This is a lot of stuff that we've covered so far. Let's look at some examples then. The Earth has an average daily distance from the sun of approximately 1.5 times 10 to the 11th meters. So what is the average daily distance that we travel? Well, we know if we're looking for average daily distance traveled, question's asking me to find my linear displacement, my linear distance, right? So I could get that. This is a daily distance. So they give me this R. They're asking me to find that daily distance traveled. Well, I can tell you this. I do know that this thing is going to travel a distance of 2 pi r in 365 days, right? Although that's not the daily distance. Wait, is that the daily distance? Yeah. Yeah. So let's do that. 2 pi times 1.5 times 10 to the 11th. That's how far I'm going to go in the year. So if I divide that by 365, that'll tell me how far I go in a day. All right. So 2 pi times 1.5 times 10 to the 11th. We're going to divide that by 365. And we get that our daily distance is going to be something crazy. 25821 30948 meters. How many millions is that? 1,000 million, 2.5, almost 2.6 billion meters a day. Dang, that is a lot. Now let's look at part B, find the average daily angular displacement. Okay, so what is the angle that I am sweeping out every day? And that's going to be a lot easier because since I already know my daily distance and I know my radius, I can use delta x equals delta theta times r and make part B a really simple problem. So let's do that. 2,582,130,948 meters. We'll set it equal to delta theta times 1.5 times 10 to the 11th meters, because that's our R. And what we get is that we sweep through an angular displacement of 0.0172 radians, which makes sense, right? Like this is a tiny, tiny amount of angle that we have swept through. And considering that we would need to do that 365 times in order to get 2 pi, that makes sense. It makes sense why this is such a little number. Let's do another quick example. I think, 1042, dang it. All right, I'm not gonna do the other example. The other example is an opportunity for you guys to do a unit conversion. You're going from RPM, which is rotations per minute, and you're doing a unit conversion to radians per second. You can check out the key to do that. In part B, you guys were taking that omega, which you had found in part A, and you were going to use V equals omega times R in order to get a linear velocity. Okay. So example 2 was just another opportunity for us to translate between, our linear quantities and our angular quantities. But in the interest of time, I'm going to leave you the task of checking this out if you feel like it would be helpful. But otherwise, I would like to get to our angular kinematic equations. Okay, much like linear kinematics were used to describe linear motion, angular kinematics are used to describe rotational motion. And they are going to use the same rules as linear kinematics, okay? So we're going to know a lot of the same concepts. Things like velocity is the derivative of the displacement. Acceleration is the derivative of the velocity. And the velocity is the integral of the acceleration. Displacement is the integral of the velocity, okay? Those are ideas that we really spent a lot of time hammering home in semester 1 when we were talking about linear kinematics. And so angular kinematics act the exact same way. And in fact, the angular kinematic equations are basically direct translations of the linear kinematic equations. So what does that mean? We in first semester establish the linear kinematic equations, things like constant velocity, delta x equals v delta t. We had things like v equals a delta t plus v naught. We had delta x equals v naught delta t plus 1/2 a delta t squared. And we also had things like final velocity is squared is equal to initial velocity squared plus 2 times acceleration times displacement, right? These look familiar to you guys, these linear kinematic equations. Now, what we could do, because we know that linear quantities can directly correlate to angular quantities, what we could do is we could take these definitions and substitute them in to our linear kinematic equations. And what you would find is that with every substitution, you had to multiply by r. And with every substitution, multiplying by r, it means that all those r's end up canceling out. And so what we are left with is we are left with four kinematic equations, or four angular kinematic equations that look basically identical to their linear counterparts. The difference being that they use angular quantities rather than linear quantities. All right. And we can use these equations exactly the same way that we used these equations when we approached problems in Unit 2. So example problems, right? Word problems like example 3. A top spins at 15 revolutions per second. It spins for 55 seconds before coming to a stop. What is the average angular acceleration of the top while it slows down? Now that reads a lot like the problems that we did in Unit 2. And if you recall, in Unit 2, the way that we solve these problems is we first wrote out all of our knowns. So we know that a top spins at 15 revolutions per second. So we know that our initial angular velocity is going to be 15 revolutions per second. I'm going to focus in revolutions per second. If you recall, we want to use radians per second, not revolutions per second. So since 1 revolution is the same thing as 2 pi radians, I know that this is actually going to be 15 revolutions per second. Oops. And if I multiply that by 2 pi radians per revolution, I should actually write down this quantity as 30 pi. I'm going to actually be using 30 pi, not 15, okay? Time it takes to slow down is 55 seconds. It comes to a stop. So my final angular velocity is 0 radians per second. And we want to know what is the average angular acceleration. So if I look at all the knowns that I have, I can identify that all of those knowns are in the equation right here. Omega equals alpha delta t plus omega naught. And so I can put in 0 as my final angular velocity. I can rewrite alpha because that is my unknown. Put in 55 as my time. Put in 30 pi as my initial angular velocity. And from there, it's all algebra, baby. We can subtract 30 pi to the other side. and get 30 pi is equal to 55 times alpha. Divide both sides by 55 in order to get alpha by itself. And when we type into our calculator 30 pi divided by 55, we end up getting that the angular acceleration of this top is 1.71. Oh, sorry, negative 1.71, because this is negative 30 pi radians per second squared. Do you guys remember that problem solving process? Yeah. Feels familiar? Okay, good. That's my hope. My hope today is that it feels like you're almost doing review when you do the problem set tonight. I would love for that to be the case, that it feels like review. Yes, it's using different letters, but your problem solving process is absolutely one that you guys have done before. You did it in first semester. You did it in unit 2 all the time, right? Let's also do part B as long as we're here. Let's draw the angular speed versus time graph of the situation, just because in unit 2 in first semester, not only did we solve a whole bunch of word problems using algebra, but we looked at tons and tons and tons of graphs, right? Because graphing motion was very important to us. So graphing rotational motion is going to be very important to us as well. So this is going to be an angular speed versus time graph. And we know that we started with an angular speed that was positive. It was about 30 pi. And we know that it ended at 0, right? So at 55 seconds, our angular velocity was now 0. And now I want you to kind of test yourself. What should the shape of this graph be that links these 2 points? Should it be linear? Should it be inverse? Should it, I don't know, look like a hunchback? Should it be a squiggly line? What do you think it should look like? I do believe it should just be a straight line. And because we know on a velocity versus time graph that the derivative is acceleration, we should know that the slope of this line should be whatever our angular acceleration was, which, if you recall, we just calculated it. It was negative 1.71. And when I look at that linear line, does that linear line look like it has a slope of negative 1.71? Probably, right? Yeah. So I think we did pretty good. I think this graph looks fantastic. Okay, and then there's another example problem in there. It is very similar in that it just allows you guys to practice reading word problems and writing out your knowns and picking out the kinematic equation, all that good stuff. On the notes key, it has this filled out. So similarly to number 2, I'm going to leave you to look at that if you think it would be helpful. In our remaining 5 minutes together, what I would like to do, I apologize again, I was a bit of a mess. I thought I had enough time and I did not. Your homework tonight, it's, oops, not this one. Here it is. Your homework tonight, it's right here. It is word problems that deal with angular kinematics. So it's things like a 0.75 meter diameter bicycle rotates through 5 revolutions in 4 seconds, what is the angular speed? 0.75 diameter bicycle wheel rotates through 2 revolutions in 4 seconds. You know, what's going to be the period? So what's the time? These are going to read very similarly to the example problems that we were able to do together. And then I have, just as we did a little bit of looking at a graph and reminding ourselves what all the pieces of a kinematics graph will tell us, I've got a couple questions for you that deal with graphs. Okay, so like I said, I highly recommend as you do this worksheet, I do highly recommend that you have your Unit 2 notes open next to you, because those notes probably go into a lot of detail about what does a speed versus time graph tell you, right? What does, here's another one, right? Here's angular velocity versus time graph. What does the slope tell you? What does the y-intercept tell you? What does the area tell you? Here's a position versus time graph, right? Like, what does the slope of a position time graph tell you? What does the area of a position time graph tell you? What does the y-axis of a position time graph tell you? Those things are going to be the same, right? Like those meanings of the graphs will be the same here for all of these angular quantities as they were for those linear quantities. Even the and I know that we didn't specifically dive into that in today's lecture, but that's because you guys already have that background knowledge. Okay. All right. Let me look and see if there's anything into the chat. Yes. Okay. So I have the notes key, and I just need to post it. And then same thing with this assignment. You guys, I have the assignment is written. I just need to post it. So I apologize again, that those two things are not immediately available to you. And yes, the key for the assignment is created. And so that's getting posted along with all of this. It's all going to go up hopefully in the 10 minutes between this class and my next class. That's the goal. Okay. What other questions do you guys have? All right.